Hi everyone, so we are at the end of semester 2. So again, we have our physics attack, also known as the physics trial for Lambda Matriculation College. So I'll be trying to do it just like any other students would. There will be no answer scheme beside me. I'll just solve it just like how we would do it. So throughout my working, I'll try to explain what am I doing, and yeah, you can just follow along. So we set a timer and we will start now. Okay, let's start with the first question. A negative 2 microcoulomb charge lies on the straight line between the 3 microcoulomb charge and the 1 microcoulomb charge. The separation between the 3 microcoulomb charge and the 1 microcoulomb charge is 4 cm. Let's try to visualize the situation first. Okay, so you would have a straight line. Okay, you will have let's use another color. Negative microcoulomb charge is lying between two charges, so in the middle you have a negative charge, and on the both side you have the 3 microcoulomb charge and also the 1 microcoulomb charge. So let's label everything. In between you have the negative 2 microcoulomb charge. On your left it can be a 3 microcoulomb charge, it can be a 1 microcoulomb charge. They didn't specify which is on the left, which is on the right? So you can put 3 microcoulomb on the left, then 1 microcoulomb on the right. You can swap the order, I think it's fine as well. You can put this as 1 microcoulomb, this is 3 microcoulomb, because they didn't specify which one is on the left, which one is on the right. Okay, but now we have sketched it already. Then they say the separation between the 3 microcoulomb and the 1 microcoulomb is 4 cm. So if you do a sketching, then that would be from end to end. This distance over here will be 4 cm. Of course, we do everything, we convert it into SI unit, so that will be meter. Okay, so let's continue to the question. Draw the position of 3 charges. Okay, that's what we have done. Show the forces acting on the negative 2 microcoulomb. Okay, so they are interested with the forces acting on the negative 2 microcoulomb charge. So technically what they are looking for is just the arrows that are coming out from this negative 2 microcoulomb charge. But since this is just us doing it on our own, so let's try to analyze all the forces acting on all the charges. Okay, to analyze forces, remember to analyze it pair by pair. Okay, what we mean by pair is when we look at one pair first, we determine whether it's attract or repel. We sketch the arrow already, then we move on to another pair. Okay, we analyze it pair by pair. Okay, before we do any analysis, let's give them names first. So let's call this Q1, let's call this Q2, let's call this Q3. Okay, now let's go. Okay, so let's start with the first pair, which is between Q1 and Q2. Q1 and Q2 are both opposite charges, so they should attract each other. So attract each other means by the forces arrow should be pointing towards each other. Okay, so you can call this a force acting by 2 on 1. By 2 on 1, this one will be by 1 on 2. 2. Okay, different lecturers, different books do it differently. Some people prefer to use on first, then followed by. Okay, in that case, they will call this as on 1 by 2, because 2 is pulling 1 to the right? So they can call this on 1 by 2. Then in that case, they can label it as F12. This one, they can label it as F on 2 by 1. Then they call this F21. Okay, it's okay to use both convention. You can call this F12, F21. You can call this F21, F12. As long as you are consistent. If you use on then by, then use on and by throughout the whole question. If you use by then on, then you use by then on throughout the whole question. You don't use F by 2 on 1 over here, but here you use F on 2 by 1. That will be a bit inconsistent, then that will be wrong. You have to be consistent with the way you put your subscript throughout the whole question. Okay, so this is fine. So let's continue. Q1 and Q3, another pair already. Q1 and Q3, they are both positive charges, so they are like charges, they should repel. So repel means point away from each other. So this force will be pointing this way, this force will be pointing this way. So we'll call this as F by 3 on 1. Okay, I keep it consistent. I start with by, then followed by on. So it's by 1 on 3. Okay, pull by 1 acting on 3. Okay, let's continue. Last we have Q2 and Q3. Q2 and Q3, the last pair. This pair here is again opposite charges, so opposite charge should attract. So you have your F So it's F by 3 on 2. This one is F by 2 on 3. So 2 is pulling 3 to the left. So that's why by 2 on 3. Okay? Whereas 3 is pulling 2 to the right. 3 is pulling 2 to the right. That's why this right arrow coming out from negative 2 microcoulomb is known as F32. Okay, we are done with the diagram, forces acting on all the charges, but they are specifically looking at negative 2 microcoulomb charge. So what you should do would be resketch everything. Okay, it's a bit of a waste of time. I have a time limit here. Okay, so you can put negative 2 microcoulomb over here, 3 microcoulomb here, 1 microcoulomb, label everything. Okay. Then they are focusing on charge forces acting on Q2, so you only need to sketch the forces acting on Q2. So this is F12, then this will be F32. Okay, that will be it. Okay, so of course you can also label this to be 0.04 meter. Okay, let's continue. Calculate the distance of the 1 microcoulomb charge from the negative 2 microcoulomb charge where the net force acting on negative 2 microcoulomb is 0. So there are two main information over here that we need to take care of. One is they ask for the distance between the 1 microcoulomb and negative 2 microcoulomb charge. So in essence, what does it mean is that they are looking for this distance over here. 1 microcoulomb and negative 2 microcoulomb means from here to here. This is what they are looking for. Okay, so I will label it as X. And after that, we also know that if this is X, then the other side of things over here will be 0.04 minus X. Okay, so they are interested with the distance over here between Q2 and Q3. But I believe if many students might label it wrongly to say it's between 1 and 2, so if they say Q1 and Q2, then label X over here, and that is incorrect. Okay, they are looking for distance between Q2 and Q3, or negative 2 microcoulomb and 1 microcoulomb. So this is the distance they are looking for. Okay, the second important information is the net force acting on negative 2 microcoulomb is 0. So the net force acting on negative 2 microcoulomb, what are the forces acting on negative 2 microcoulomb? F12 and F32. F12 and F32. So these two forces will have to balance each other in order for a net force to be equal to 0. Net force is equal to 0 means that F12 and F32 point opposite direction, but they should have the same magnitude. Okay, so let's try to determine it. Okay, we mentioned just now that the net force acting on 2 is equal to 0. Okay, so that is the mathematical way of writing it. We know there's x-axis and y-axis, x component, y component, but in this case everything is in the x component, so I can call it as sum of force acting on 2 in the x component is equal to 0. Okay, so what is in the x component for our diagram over here? You have F12 pointing to the left and F32 pointing to the right. So pointing to the left would be negative, so negative F12. Pointing to the right will be positive, so F32. Okay, you should not put any vector arrow on top because you have already considered direction using the sign already. So this is just the magnitude of force, no arrow on top. Okay, let's continue. We bring things around, shift things around. That will be F32 equals to F12. And therefore we can open it up, use which equation? Well, you can use the first equation to determine the force. There's also second equation which involve force, but for this situation the first one will be more appropriate because it's in between 2 point charges. But to be careful, when you're using equation 1 until equation 3, please make sure you modulus your Q or you modulus your Q, because the sign should not be included for your charges. So I think it's recommended to put on the modular sign. Okay, but let's continue. Okay, so I can call it as K modulus Q3 modulus Q2 divided by R23 square. So we call as K modulus Q1 modulus Q2 divided by R12 square. Okay, so I believe you can see that some things can be crossed out over here. The K can be crossed out, the Q2 can be crossed out, so we are left with Q1 and Q3 as a numerator on both sides. Okay, so we can do substitution maybe. Q3 it's 1 microcoulomb. Again, don't substitute in the sign for your charges, just leave it as like this. Okay, it's equals to, okay, let's write the numerator first. Q1 is 3 microcoulomb. Okay, R23 is between Q2 and Q3, and that's what we call as X, right? Okay, so R23 is called as X. Okay, then the other side will be 0.04 minus X square. Okay, I believe at this point you will notice that something can be crossed out as well. The micro over here can be crossed out. So you will be left with okay, cross multiply this equation, you get 3x squared on this side, you get 0.04 minus x squared this side. Okay, continue, you can open it up. Okay, one, two, three, 0.0016 negative 0.08x plus x squared is equals to 3x squared. So if you shift everything, you get 2x squared plus 0.08x and minus 0.0016. Okay, so let's try to determine x. Okay, as I said earlier, I'm doing it without an answer scheme, so everything here is live. Okay, 0.0016. Okay, you have two answers because this is quadratic, 0.0146 meter, and also another one would be negative 0.0546 meter. Okay, we'll be rejecting this equation because I believe we are looking for a positive value of x. Okay, if it's negative, right, then what it might mean is that this distance over here, this charge over here might need to be brought somewhere else. Okay, I'm not really sure right now, but I'm very confident that this positive answer is the answer. If it's negative, what does it mean? It might be somewhere not between Q1 and Q3. Not really sure, but I think we have time limit here. I'm not able to think through this thing. Okay, so let's just leave it as this. So the distance between Q2 and Q3 is 0.0146. Then if you take 0.0146, you take 0.04 minus it, there will be the distance between Q1 and Q2. So we are done. Let's move on to the next part of question 1. Question B. Let's zoom in. Okay, 2-point charges Q1 and Q2. Q1 is positive 3 microcoulomb, Q2 is negative 5 microcoulomb, are placed at two corners of the triangle of sides 0.3, 0.4 and 0.5 meter as shown in figure 1. P is the third corner of the triangle. Okay, they didn't specify anything whether, but in the diagram they did specify it's a right angle triangle, and also you can see it follows Pythagoras theorem. There's 3, there's 4, there's 5 over here. Okay, so first thing, calculate electric potential at P. Okay, so you see that they are looking for electric potential. Electric potential is V, and when you see the question asking for electric potential, you have to look for the location. Okay, where? Okay, every time when they look for electric potential, they must specify a location, and in this specific question, the location will be P. So because the location is P, this will be the location of interest. Okay, so every time we have already specified where's the location of interest, let's check first who is producing the electric potential over here, who is interacting with the electric potential over here at P. Okay, as you can see, the surrounding charges are Q1 and Q2. So Q1 and Q2 will be responsible for producing the electric potential at point P. So it means by if you see an electric potential at point P, the electric potential is happens or occurred or exists due to Q1 and Q2. Okay, but who is interacting with the electric potential at P? You have to place a charge at P in order for the charge to interact with the electric potential at point P. So since there's nothing being placed at point P, we'll say that no charges is interacting with the electric potential at point P. So this is there's two charges producing the electric potential, but no charge is interacting with the electric potential. So because this situation has no charge interacting, we'll be solving the question for 1 using the produce equation. Okay, if you are in my class, right, equation 2 is an interact equation. Means by this question, right, you are focusing on the charge interacting. Okay, if you are using this equation with a big Q, then this is for the charge that is producing the electric field. Okay, so for this situation, it's a small q, so this one is the charge interacting with the potential. This is the charge that is producing the potential. Okay, so because we are looking for V, so this is our equation because we are looking for produce. Okay, so we're looking for produce, so V is equals to KQ over R. Okay, so when I'm going to use this equation, what I usually tell my student to do is to first thing is to sketch spring. From all producing charges. Okay, you sketch the spring from all producing charges to the location of interest. In this case, it's P. Okay, so there are two charges here. There will be two springs. One spring from Q1 to P, and another spring from Q2 to P. Okay, so besides that, I'm going to ask them to label the spring as well. Label based on this equation. Okay, so this one will be K, which Q, Q1, which R between 1 and P. Okay, what about this spring? This will be K, Q2. This will be distance between 2 and P. Do you need to modulus a Q? No, because only the first three equation requires you to modulus your Q. But 4 until 8, those are scalar values, scalar quantity. Your charge, the sign is important. You still need to put it in, so you don't need to modulus your charge. Okay, so let's start. Okay, then what do we do after that? We add on all the labels that we have already labeled just now. So V at P will be K Q1 R1P plus K Q2 R2P. So we are going to substitute in everything, but I think you can see that we can factorize it out first, the K, then that will leave us with KQ1 over R1P plus KQ2 over R2P. Okay, so this will be 9 times 10 to the power of 9. Q1, how much is Q1? 3 microcoulomb. So 3 times 10 to the power of -6. R1P, 1 and P, the distance between them is 0.30. Okay, let's continue. Then you have your Q2. Q2, remember to put in the sign, -5 microcoulomb. Then the distance between 2 and P, the distance is 0.5. So this will be 0.50. There's no square here. This is electric potential. This is not electric field. Okay, so you can do your calculation. Okay. Okay, very nicely, nice answer, 0. Okay, so the electric potential at P will be equals to 0. Okay, next, the work needed to bring a test charge Q naught from infinity to P. Okay, so when you see there's work needed, if you see the question involve work requires you to determine from where to where first. Okay, you need to be very careful to look through the question to understand the charge move from where to where. Okay, then which charge is moving? Okay, so to answer the first question, from where to where? Well, infinity to P. So our initial is infinity, our final is P. Okay, that is very important. Second question, which charge is moving? To bring a test charge from infinity to P. So this is the moving charge. Okay, once we are clear with this, then we can proceed to solve the question. Okay, here's something that might be a little bit different. Okay, in my class, I don't really use this equation exactly. What I do is I ask my student to modify it to become, if it's a work elect, then it's equals to negative delta U, also known as negative Q delta V. Okay, whereas if it's work external or work required or work done or work external, work done by external force, it's delta U, it's Q delta V. Okay, most of the time in our syllabus we are focused on this one, not really on this one. Okay, most of the time it's external force, work done by external force. So we can say the difference is, instead of putting it as a V, we're putting it as delta V. Why do we put it as delta V? Because this one is not exactly a potential at one point. It's this V here actually represent potential difference. It's from somewhere to somewhere. There's an initial, there's a final. You take final minus initial. So that's why I changed it to delta V, so that it reminds us that there's final, there's initial for this equation over here. And you need to find the difference between the final and initial. Okay, so I'll be using this equation down here. Okay, so work external, and usually I ask my student to also write from where to where, so I move from infinity to P. Okay, it's equals to Q delta V. Okay, so let's check first which this Q here will represent the moving charge or the interacting charge. Okay, the interacting charge is the moving charge. So in this case, the moving charge will be Q naught. Okay, then next delta V here will be V final minus V initial. So our final is P, our initial is infinity. Okay, this one is your final, this one is your initial. Okay, so we know that V at infinity is equal to 0. This is just concept. At infinity, your electric potential is equal to 0. So that makes our equation to become Q naught multiplied by Vp. So Q naught is positive 1.00 times 10 to the power negative 6. Vp is equals to 0. That's what we say, calculated in question 1. So if you put in everything, the answer will be 0. So your external work done by external force is equals to 0 joule. So the work needed to bring a test charge from infinity to P will be 0 joule. Okay, so that's it. That's it for question 1. Let's move on to question 2. Okay, so you are given a circuit over here which has 3 capacitors connected in parallel, and it's connected also to a battery. So figure 2 shows an arrangement of 3 capacitors, 2 microfarad, 3 microfarad, and 4 microfarad connected to a battery. If the charge on the 2 microfarad capacitor is equals to 3 microcoulomb, calculate the voltage across the 4 microfarad capacitor, the charge across the 4 microfarad capacitor, and also total energy. Okay, this is a very typical series and parallel question. So what I told my students usually is, if it's a series and parallel question, okay, if it does not involve more than one battery, if there's only one battery or there's no battery, any series of parallel question, right, you have to solve it using a technique using you combine, then you reverse. Okay, this is a very standard steps of doing things. Combine means by you find the equivalence capacitance. Then after that you reverse. Okay, you reverse step. There's nothing much to explain here. Okay, let me demonstrate to you how to do it. Okay, I'm not going to focus on what the question asks for. I'm going to fully analyze the question. Then I'll tell you in the exam setting how can you do it faster. Okay, so what I'm going to do is I'm going to figure out how should I combine all the capacitors to become one. Okay, the current diagram given here is 3 capacitors all connected in parallel. And it's connected to a battery. Okay, so I can call it's 2, 3, 4. Okay, so 2 microfarad, 3 microfarad, 4 microfarad. Then this is the battery. Do they specify what is the battery voltage? They didn't specify. Did they specify? Let me double check first. Where's the question? Battery. Weird. Okay, they really didn't specify what the battery voltage is, but never mind. I think we can manage with that. Okay, never mind. Okay, let's continue. Okay, so what I'm going to do now is I'm going to give them names. Okay, every time you do combine and reverse, make sure to give them names. So I can call it as C1. Okay, capacitance 1, capacitance 2, capacitance 3. Okay, what my students sometimes do is they see 2, 3, 4. Right? They call it as C2, C3, C4. It makes it easier to do your substitution. Okay, but intuitively we'll call it C1, C2, C3. Okay, but I don't think it's wrong to call it C2, C3, C4. I think it's fine as well. Okay, so we are going to combine it. So what we can do is we know that C1, C2, C3 should combine in parallel. So combine it in parallel, you get it to become one single capacitor connected to a battery. Okay, so because you combine everything, this one will be called as C123. Every time you combine, just combine the subscript. Here the subscript is 123, so you combine it with 123. Okay, so it's parallel, so we know from the equation, if it's parallel, you use normal addition. This equation is for series, this equation is for parallel. Okay, so let's go. Okay, so C123 here will be equals to just C1 plus C2 plus C3. Okay, so C1 plus C2 plus C3, that will be 2 microfarad plus 3 microfarad plus 4 microfarad. Remember to write down the micro. You can write it in exponent, you can write it in symbol mu, that's fine. I think both of them are accepted. And at the end, remember to attach also the unit, which is farad. So the equivalent capacitance is 9 microfarad. Okay, let me put on the value Q1 here is equals to 3 microcoulomb. 30 microcoulomb, sorry. Okay, now we are done with step 1. This is called combine. Now we move on to reverse. Okay, so how does reverse work? We move from the last diagram, which is the diagram, the rightmost diagram. We reverse the diagram back towards the leftmost diagram. Okay, if there's 3 diagram, you have to reverse it sequentially. Means by you move from the rightmost diagram to the second rightmost diagram to the third rightmost diagram, slowly move to the leftmost diagram. But since there's only 2 diagram over here, you just flip the order over here. Okay. So battery. Okay, this one is C1, C2, C3. This one will be V. Okay, this one will be C123. This one is V. Okay, so let's start. From the leftmost diagram, make sure you are able to determine C123, V123, and also Q123. Okay, C123, we know that is 9 microfarad. V123, we are not sure about it because they didn't let us know what is the battery connected to, what voltage is it, so we don't have V123. So let's continue Q123. If you don't have V123, technically that means you cannot find Q123 because Q123, it's the, you can obtain it using Q is equal to CV, but there's no V, so you cannot find Q. But never mind, let's move on to the next diagram. Next diagram, we are breaking C123 to become C1, C2, C3, and that's breaking up the capacitors in parallel. So we know that in parallel, what should happen is the voltage should be the same for all the capacitors in parallel. So we know that V1 will be equals to V2, will be equals to V3, and that's equals to V123, and we don't know the value. Okay, but we know that Q1 plus Q2 plus Q3 is equals to Q123. Okay, that value we are not really sure. Okay, so from here, okay, I'm not sure whether you have the background for this or not, but if it's a series circuit, Q is constant, whereas the V adds up. Okay, if it's a parallel circuit, if it's capacitors connected in parallel, the V will be constant instead, and then the Q will add up. Okay, so that's what I mean over here. Okay, so technically you can find 3 values over here. You can try to find Q1, Q2, and Q3. Okay, let me demonstrate how to do it. Q1 will be equals to C1 multiplied by V1. Okay, so do I have C1? I have C1. C1 is 2 microfarad. Do I have V1? V1 I don't have it, but I have Q1. So Q1 is 30 microcoulomb. C1 is 2 microcoulomb. So from here I find V1. So from here I can see that V1 is equals to 15 volt. And because V1 is equals to 15 volt, V2 is the same as V1, V3 is the same as V1, V123 is the same as V1. So everybody is 15 volt. Okay, so now because I know that everybody is 15 volt, I can say V123 here is 15 volt. So from here, I'm able to, okay, you can do CV right now. Okay, C123 is 9 microfarad. V123 is 15. So you can get this to be equals to 135 microcoulomb. Okay, continue. You try to find everything. Okay, Q2 is equal to C2 multiplied by V2. Q2 don't have the value, but C2 will have the value is 3 microfarad. V2 is the same as V1, same as V3, so it's equal to 15. So the answer would be 45 microcoulomb, whereas Q3 is equals to C3 multiplied by V3. C3 is equals to 4 microfarad. Q3 is the same as V1 and V2. V3 is the same as V1 and V2. So that's 15. So Q3 is 60 microcoulomb. Okay, so from here effectively I find everything. Okay, even though it's needed or not needed, I really find everything already. As you can see, I have my C123, V123, Q123. I have my Q1, Q2, Q3. All value is known: 30 microcoulomb, 45 microcoulomb, 60 microcoulomb. And if you add up 30 microcoulomb, 45 microcoulomb, and 60 microcoulomb, I believe you get 135 microcoulomb. Okay, I also have V1, V2, V3. All of them should be equals to 15. Okay, so technically I get all the voltage, I get all the charges. It's a bit too much, okay, because the question doesn't ask for everything. But this way of systematically analyzing the question, starting from combine, then reverse, allows you to obtain all the charges and all the potential difference for each of the capacitors in the circuit. No matter it's just pure parallel, pure series, or series parallel, it will allow you to find everything. Okay, so let's focus on the question right now. First question asks for voltage across a 4 microfarad capacitor. 4 microfarad over here is known as C3. They ask for voltage, so technically that means V3. Okay, V3 over here we know that it's 15. That's what we know from the question. V3 is equals to 15 volt. Okay, next question. The charge across the 4 microfarad capacitor. 4 microfarad again is C3, charge is Q, so they're asking for Q3. Okay, what is Q3? Look back into our analysis. Q3, Q1, Q2, Q3. Okay, so Q3 is over here. Q3 is 60 microcoulomb. Okay, last question. What is the total energy stored in a capacitor? Okay, energy stored, if you look back into the equation, energy stored will be this equation over here. You can use either of this, half CV squared, half QV, or half Q squared over C. All of them can be used as long as you use the overall Q, C, and V. What do I mean is, if you look for total, that's 1, 2, 3, everything combined. So half CV squared, you can use half CV squared, combine everything. Okay, if you prefer to use half QV, also okay, but you must use half QV. Okay, and also the same thing will be for Q squared over C. Okay, any of these can be used. Okay, I'll be using the first one. So half C123 is 9 microfarad. 123 is 5. V123 is 5. So if I calculate it, I believe (1.01 times 10 to the power negative 3) energy is joule. Okay, so that's the total energy stored in the capacitor. Okay, so that's how I do question 2a. Let's move on to question 2b. Okay, 2b shows a current discharging or discharging, we're not sure. Okay, but the current decreased from I0 falling through time. Okay, and at 10 seconds, they specify that the current is at 0.37 I0. Okay, 0.37 is a very important value. 0.37 is the same as e to the power of negative 1. Okay, so I believe if you can do a bit of recall, the definition for time constant, okay, if you are focusing on current, okay, then it's the time taken for the current. Okay, current both for charging and discharging, current will decrease with time. Okay, so you can say the time taken for the current in the charging or the discharging circuit. Both are fine because both of them, the current drops with time. Okay, current in the charging or discharging circuit to drop to 0.37. Okay, i.e. 0.37 is found using E negative 1 here. Okay, drop to 0.37 of its initial value. Initial value is what? I0, no? Okay. Okay, if you are using charge, then it's different. For current, both charging and discharging circuit decrease with time, so there's no problem to write it like this. But if it's charge, time taken, let's say if you're looking at charge, right? So time taken for the charge in the discharging circuit dropped to 0.37. But if it's charging goes up, right? Okay, if it goes up, then time constant is at the point where it's 0.63 of Q naught or 0.63 of V naught. Okay, this is charging. Okay, if it's discharging, the graph will be like this, right? If it's this kind of graph, then we look for 0.37 Q naught or 0.37 V naught. This is discharging. Okay, that's the idea of tau. Okay, yeah, you can look more into the theory in your reference book. Okay, so right now, because they specified it 0.37, we know that 0.37 here, this value here will be tau. Okay, tau is the time taken, 10 seconds, for the charging or discharging circuit to drop to 0.37 of its initial value. So this is actually the time constant. Okay, no matter it's a charging or discharging circuit, this is the time constant, because charging, discharging, they both decrease with time. Okay, figure 3 shows the variation of the current in a circuit with time during a discharging process of a capacitor through a resistor of 2 mega ohm. So your resistor is 2 mega ohm here. Okay, so let's write down 2 is time, mega is times 10 to the power 6 ohm. Okay, determine the time constant. Just now I already mentioned it already. From the graph, you see that tau is equals to 10 seconds. Just writing it like this, I think you'll be able to get your marks ready, because it's very straightforward. Second question, they ask for the capacitance. Okay, we know that time constant can be related to the capacitance through tau is equals to RC. So tau is equals to RC. Okay, R will be 2 times 10 to the power of 6. C, tau will be 10 seconds. So from here, you can find your capacitance to be equals to 5 times 10 to the power of 6. So that's 5 microunit farad. Okay, so that's the capacitance of the capacitor in this discharging circuit. Okay, so discharging circuit, you don't have battery, you just have a resistor and also a capacitor. Okay, in this case, the resistor is 2 mega ohm, the capacitance is 5 microfarad. Then this discharging here has a time constant of 10 seconds. This discharging circuit has a time constant of 10 seconds. Okay, let's continue. Question 3. A wire 5 meter long and 3 millimeter in diameter has resistance of 100 ohm. A 15 volt potential difference is applied across the wire. Okay, so to sketch the situation, let's say you have a wire over here. This wire here, if you measure the length of this wire, it will be 5 meter long. But if you measure the diameter over here, this diameter here will be 3 millimeter. Okay, then they say that the resistance is 100 ohm. And you're going to connect this wire here to a 15 volt potential. Okay, so this battery here is 15 volt potential. Okay, first thing first, they ask for the current in the wire. Okay, I think this one probably a bit straightforward. Why is it straightforward? Because V is equals to IR. You know the resistance across the wire. You know the potential difference applied across the wire, so you can find the rate of flow of charge, okay, or the current flowing through the wire. So this is 15 volt, current, resistance is 100. So from here, you know that your current is 0.15. Unit for current is ampere or coulomb per second. Next, the resistivity of the wire. Okay, you are given the length, you are given the diameter. This is diameter, but you can use it to find the area. So you have the area, you have the length. Well, that helps you to know that how do you relate between the resistance, the resistivity, the area, and the length. Well, these are the factors that affect resistance. Okay, so chapter 3, this set of equation, to relate everything together, this will be the equation. But usually I prefer to write it this way. R is equals to rho L over A. Because resistance depends on three factors: the resistivity of the material. Hey, what am I doing? Resistivity of the material, the length of the conductor, and also the cross-sectional area of the conductor. So these are factors affecting resistance. Okay, this is how I usually arrange it, but for this situation, we are going to rearrange it into this form because this is what they're asking for, right? They're asking for the resistivity rho. Okay, so rho will be equals to RA over L. Resistance is given as 100 ohm. The cross-section area, you can find it using, because it's diameter given, you can use it to find area. This is pi r square, but r is essentially just diameter divided by 2. Then you get radius, but this needs to be square. Okay, so pi r square divided by the length. Length, 5 meter. Okay, let's submit everything now. So 100 pi, diameter is 3 mm, convert it into meter, that will be times 10 to the power of -3 divided by 2 square divided by 5. Okay, be very careful with the prefix. Many students have careless mistakes when it comes to the prefix. Okay, so what I get here is 1 point, oops, it's right here, 1.414 times 10 to the power -4. Okay, how many decimal places is not really important. Usually you put 2, sometimes up to 3, it's really up to you. Okay, but don't leave too little. Don't write just 1 or 1.4. Just leave it 2 decimal places usually. Okay, usually it should, the proper way is to follow significant figure, but for our matriculation level is usually just how many decimal places, usually 2 or 3. Okay, so this unit is ohm meter. For resistivity is ohm meter. Okay, next, the rate at which heat is being produced. Okay, so rate at which heat is being produced. Heat is the form of energy. So when you look at energy, rate means by per unit time. So energy per unit time is basically just power. Okay, so they are looking for power over here. Rate means per unit time. Heat is a form of energy. Energy per unit time is just power. So power, there are 3 different equations you can select. You can use VI, you can use V square over R, you can use I square R. Okay, all these are valid, and I think you can use any one of them. You can find the equation over here. P is equal to IV, I square R, and V square R. Same thing. Okay, I'll use the one VI, okay, over here. You don't need to write the others if you are not using it. So V is 15, I here is 0.15. Okay, so if you find the power, that will be 2.25 watt. Okay, unit for power is watt here. Okay, don't write joule. Okay, joule per second is acceptable, but yeah, usually write as watt. Okay, so done with part A already. Let's move to part B. Part B over here. A car battery has an EMF of 12 volt. Okay, so you can probably label it here. EMF here is 12 volt. Internal resistance of 1 ohm. So this is internal resistance of 1 ohm. The external resistor has a resistance of 5 ohm. R is equal to 5 ohm. Okay, connected in series to the battery as shown in figure 4. Determine the reading of ammeter and the reading of voltmeter if both meters are ideal. So this one looking for current, this one looking for terminal voltage. Okay, so how do you relate everything together? You have this equation, I think. Okay, there's many ways of writing it. Okay, basically this is the energy supplied by battery. Okay, per unit time. Energy supplied by battery per unit time. This one is the energy consumed by the battery per unit time. Because battery is made of certain material, right? So the material will pose some form of internal resistance. So for the charge to get through the battery, they will have to use up some energy also. So this is the energy consumed by the battery per unit time. So this is what's left lah. what's left for the external circuit. Okay. Many ways of thinking about it. This is how much money your mother gives you per day. This is how much money you spend in the canteen. This is how much money that is left that you can put it into your what do you call it, piggy bank. Okay, the idea is something like this. Okay, so there's many ways of rearranging it. You know that this terminal voltage here can be expressed as IR, but this one is R, but this one you have to be very specific. This is R effective. Basically everything outside the battery, all the resistance outside the battery, if you combine them, you get R effective over here. Okay, so I believe for this situation here, you have your R, you have your big R, small r, there's only one resistor outside, so R effective over here is just this R over here. You have 2R, done. You have also this EMF here, so what's left is just a current. Okay, so I think that's the reading of the ammeter, right? Okay, let's factorize all the current, so this will be R plus R effective. Okay, your EMF is 12 volt, your current R internal resistance is 1.0, that is inside the battery. Outside the battery with your external resistance, which is 5. So if you calculate it, I believe your current will be 2.0 ampere. Okay, this equation comes from this one, this equation over here. Okay, but they don't write down the other version of it. The other version of it is epsilon is equals to IR plus R effective external circuit. Okay, so let's continue. Okay, so that is the reading of ammeter. This is done. Now we want the reading of voltmeter. Reading of voltmeter reads the terminal voltage. So terminal voltage we mentioned just now is V is equals to IR. Your current is 2.0. It's the same current because this is a series circuit, right? So technically what passed through inside the battery and what passed through outside the battery, the rate of flow of charge or the current are the same. Okay, so no problem writing it as 2 ampere. Then the resistance outside is 5. So 2 times 5 is basically just 10.0 volt. So that is your reading of a voltmeter done. Okay, so that's part B. Let's continue to part C. Okay, to put a bit of context here, the battery provides 12 joule of energy per second. Provide 12 joule of energy per second. 10 joule will be used in outside the circuit. So means by 2 joule will be consumed by the battery itself. Okay, 12 joule provided by the battery per second. 2 joule will be lost to the battery per second. You are left with 10 joule to be provided to the external circuit every second. Okay, next question. From figure 5, battery P with EMF of 1.3 volt. Okay, that's label. This one is 1.3 volt. Internal resistance of 2 ohm. So this one is 2 ohm. Battery Q has EMF of 1.5 volt. Internal resistance of 0.8 ohm. And also a resistor 4. They are connected in parallel. Calculate the current in battery P, battery Q, and the 4 ohm resistor. So they are looking for current. So I'll be calling the current in battery P as IP, current in battery Q as IQ, and current here as I or IR, PQR, right? Okay. So this is a Kirchhoff rule question. Immediately you can see it's a Kirchhoff rule question. Why? Because there's more than one battery. Every time the question involves more than one battery, immediately it will be a Kirchhoff question. Okay, because you cannot solve it using combine and reverse. You have to solve it using Kirchhoff. Okay. So Kirchhoff, usually I do it in a 5-step process. So first step will be to label all components. Second step will be to check the current at junction. Okay, once everything is logical, then we proceed to do your junction rule. Junction rule usually one equation, usually not necessarily. Loop rule usually there's two equations, also not necessarily true, sometimes just one is enough. Last step, you do your substitution, you arrange your equation, then you solve your equation, usually using calculator. Okay, so let's start with step 1. We label everything first. So I think most of the things are nicely labeled. Epsilon P, Epsilon Q, RP, RQ, and R. All these components have their own name already. Technically, part 1 is done. Okay, next part, check current at junction. So how many junction do we have? This is not a junction, this is just a band. This is a junction, this is a junction. So there are two junctions. This is not junction yet, just these two only. So what do you check? You check the current. So look over here. Is there any current flow indicated in the diagram? Well, they didn't indicate any kind of current flow, right? So we have to be the one to assume a direction for the current. Okay, it's up to you how you want to assume it, as long as it's logical. Okay, so let's say if I choose to have current flowing this way, I have to be consistent. If I'm flowing this way upwards, impossible there's current flowing rightwards. Okay, it has to follow a certain direction. Okay, along this path they should be in the same direction. Okay, so this path over here I'll call it as IP. Okay, and the direction should be consistent from one junction to another junction. So let's say from this junction to that junction, it has to consistent in one direction. You cannot have one side going this way and another side going this way. So this is logical. Okay, second path between two junctions, this junction and this junction, and another path is this path over here. Okay, so again, we assume a direction. Any direction will be fine as long as you don't make it, you don't mess it up. What I'm trying to say, not mess it up, is you don't put one direction over here, another one like this. Then there will be conflicting already because they will collide in the middle. It doesn't make sense. Okay, so the current should be flowing in a consistent direction. So if I put it to be to the right, then it has to be to the right along the way. Okay, last one over here, if I put it to be downward, then this will be along this direction. Okay, you can make it flowing from here to here, that's fine as well. You pick yourself, but it has to be consistent throughout the path. Okay, so let's label and give them names. IP, this one I call it as IQ, then this one is called as IR. Okay, because that's current flowing through battery P, right? Current flowing through battery P, then we call it IP. Current flowing through battery Q, I call it IQ. 4 ohm resistor, this is the 4 ohm resistor, I call it IR. Okay, when I say check current at junction, whether it's logical or not, okay, you need to check whether it's logical or not. What does logical means, right? You focus on one of the junction, you have to see, is it all in or all out? If it's all in or all out, right, then these are illogical. Then that means that you cannot proceed. Okay, you have to be some in, some out. Then that will be logical. Means that there's some current flowing into the junction, there's some current flowing out of the junction. Okay, in this case, you can see that IP is flowing into the junction, entering the junction, but IQ and IR are both flowing out of the junction. So in that case, it's logical because you have one current flowing in, you have two current flowing out. That's logical. If it's illogical, it will be 3 current flowing in, no current flowing out, or 3 current flowing out, no current flowing in. Then that will be illogical. But this case is logical. So we can say that we're done with step 2 because it's logical. Next, we will do junction rule. Okay. So junction rule. Junction rule, look at one of the junction, will be fine. Let's look at the left junction. So sum of I is equal to 0. So in this case, what is flowing in will be positive, what is flowing out will be negative. IP is flowing into the junction, so that is positive. IQ will be flowing out of the junction, so that will be negative. Next, IR. IR is flowing out of the junction, so that is negative as well. Okay, so we build our equation for junction. Okay, done. Next, we move on to loop rule. Loop rule, in this case, if you look at the diagram, there are 3 loops available. You can do it for this loop over here, you can do it for this loop over here, or you can do it for this loop over here. Okay, up to you which one to choose. Okay, so I'm going to do this loop and this loop over here. Okay, so let's label it clearly. What are the loops over here? So my first loop, I'll be doing it from here to here. I'll call this as loop 1. Okay, my second loop will be going from here to here. I'll be calling this as loop 2. It's up to you. You can choose to do it clockwise, you can choose to do it anti-clockwise. It's really up to you. Okay, so I'll be doing it the way I teach it in class. Okay, which is sum of V is equal to 0. If it's a resistor, okay, if your direction of loop follows current, that's a normal way of flowing. It's normal. So normal, you lose energy. That's why it's negative. On the other hand, if the direction of your loop opposes the current, then that is an abnormal way for current to flow. So abnormal way of flowing through resistor, abnormal way of energy change is you gain energy. Because usually if you have current flowing through resistor, your current will lose energy to give to the resistor. That's why technically you should lose energy for the normal way. So abnormal will be gaining energy. So gaining energy will be positive. Okay, it's true concepts. If you have current flowing through resistor, the current should give energy to the resistor. Okay, because current give energy, the current will lose energy. The current lose energy, that's why it's loss of energy, negative. Okay, so abnormal way, the opposite way will be gain, so that's why positive. Okay, on the other hand, for your EMF, if you enter the negative but you exit at the positive, that's the normal way of doing things. Okay, normal way of current flowing through battery. If your current flow through battery, the current will gain energy. So this is positive. Okay, on the other hand, if you enter through the positive terminal, you exit through the negative terminal, that's abnormal. So abnormal means by you will lose energy. Lose energy means negative. Okay, because every current, if you flow through the battery, technically you are getting energy from the battery. So if you are getting energy from the battery, technically you should gain energy. So that's positive. Okay, but if you are going in the reverse direction, means when you enter through the positive terminal, you exit through the negative terminal. But normal way, you lose energy. That's why it's negative. Okay, to explain this a bit further, any kind of circuit, this is your battery, this is your light bulb, your current flow this way, right? So technically inside the battery, it should go from negative to positive inside the battery. So this is normal. Normal to go from negative to positive in the battery. Okay? Okay, done. So let's go through loop 1 first. Okay, loop 1, we are going to start from here. First thing we see is the resistor. Resistor, look at whether the direction of loop follows or opposes current. Current is to the left. My loop is also going to the left. Okay, my loop is like this, so it's going to the left. My current is also going to the left. Both are left over here, so that means it's normal. Normal means by you lose energy. So lose energy, negative. Which current? Current is IP. Which resistor? Resistor is RP. How do I know it's IP? Because from here to here should be the same current. From this junction to this junction, all the same current. So here should be IP as well. Okay, continue. The next thing I pass through is the battery. My loop is going through the negative first, then it exit at the positive. Enter negative, exit positive. That's normal. Gain energy, so positive. So positive epsilon P. Continue. I'm going down, going through here. So the next thing that I see is this battery over here, the EMF. I'm entering the positive terminal. I'm exiting the negative terminal. So that's the enter positive, exit negative. Normal way, lose energy, negative. So negative epsilon Q. Continue. I'm going through this resistor over here. My current is flowing to the right. My loop over here also going to the right. Okay. Current going to the right. Loop also going to the right. So that means that it's following the direction of current. So following direction of current, that's normal. Lose energy, negative. Negative IQ RQ. Why IQ RQ? Because the whole path from this junction to this junction, this whole path here, it's IQ, going from left to right. Okay, equals to 0. Okay, so that's loop 1. Let's do it for loop 2 as well. Okay, loop 2, I'm going from here to here. Okay, so first thing I pass through is RQ. So RQ here, my current is flowing to the right, but my loop is going to the left. So right and left, they are called opposite direction. So opposite direction, you are supposed to gain energy. So gain energy is positive. Okay, so positive IQ RQ. Okay, next I'm going to continue, move on to EMF Q. Okay, epsilon Q. I'm going to pass through the negative first, followed by the positive. Negative first, then positive. Negative first, then positive. So enter negative, exit positive. This is normal. You gain energy, so this is positive. Okay. So positive epsilon Q. Continue. Next, you follow through the path until you reach this point. Resistor R. Resistor R, your loop is going to the right, and your current is also going to the right. That means it follows. Follow is normal. You lose energy. That's why it's negative. So negative IR multiplied by R. Okay, then last thing you do, you continue your journey, then you come back to the point where you start. Okay, so if you come back to the point where you start, then it equals to 0. Okay, so we are done with step 4 over here. Last step, we do our substitution, then we arrange our equation, then we solve it. So how do we substitute? Okay, well, there's nothing to substitute over here. Nothing to substitute is P, Q, and R. Loop 1, we have R, epsilon, epsilon Q, and RQ to substitute. Let's do it. Negative IP, we don't know. RP, we know it's 1.3. Epsilon P, it's what am I doing? Sorry. IP, it's 2. RP is 1.3. Minus epsilon Q is 1.5 minus IQ RQ. RQ is 0.8 equals to 0. Okay, so when I say arrange, right, what should arrange is arrange as IP, IQ, IR equals to 0. So how much do you have for IP? IP is over here, negative 2. So negative 2. What do you have for IQ? Negative 0.8. Negative 0.8. What do you have for IR? There's no IR in this equation, so there will be plus 0 IR. Then the rest of the stuff, or you can call it as the constants without unknown, those you put it on the right hand side over here. So 1.3 and 1.5, if you calculate it, you get negative 0.2. Shift it to the right, you'll get positive 0.2. So this is your equation. Okay, this is how you arrange it. Okay, let's continue for the next equation down here. Loop 2, you can do your substitution now. positive IQ, RQ it's 0.8 plus epsilon Q is 1.5 minus IR we don't know, R is 4. Okay, equals to 0. Again, we arrange it. You have IP, IQ, and IR. What do you have for IP? There's nothing for IP, so that's 0. What do you have for IQ? IQ, you have one of this, 0.8 positive plus 0.8 IQ. Then next, you have your IR. IR is over here, that's negative 4. So, negative 4. Okay, then the rest of the stuff, you bring it to the right. That's 1.5. Shift it to the right, you get negative 1.5. Okay, so that's how you arrange your equation. Okay, so once you have arranged your equation, bring everything together. IP, IQ, IR, be too close together. IP, IQ, IR, IP, IQ, IR, IP, IQ, IR. What do I do? IP, it's how much? IP, it's plus, then negative plus 1, negative 1, negative 1. What am I referring to? I'm referring over here. Plus 1, negative 1, negative 1. Okay, and equals to 0. Next equation is over here. Negative 2, negative 0.8 plus 0 equals to 0.2. Next equation over here, 0, 0.8, negative 4, negative 1.5. Just write it here. Oops. Zero, positive 0.8, negative 4, negative 1.5. Okay, so you can use your calculator to solve this. You don't need to do a substitution on your own. If you are using this calculator, FX570ES, you can press mode, then you pick number 5 equation, then you can press number 2, ANX plus BNY plus CNZ equals to DN. Okay, you can choose mode number 2 inside your equation mode. Okay, so you have A, B, C, D on your column and you have 1, 2, 3 on your rows. So what you can do is just put in everything. Okay, A, B, C, D, 1, 2, 3. Okay, so just put it in. 1, negative 1, negative 1, 0. Negative 2, negative 0.8, 0, 0.2, 0, 0.8, negative 4, negative 1.5. Okay, so you get your answer. Let me write it down. You get IP is equals to 3/160 ampere, which is equivalent to 0.0188 ampere. IQ is equals to negative 19/64 ampere. That's equals to 0.2969 ampere. IR or I be equals to 101,320. That's equals to 0.3156 ampere. Okay, write it 3 decimal place. I think it's enough. 4 is a bit too much, but that's basically it. Okay, remember negative sign. Okay, so if you are using a different current direction, let's say you assume IP to flow this way, then your answer will be an opposite sign to mine. Okay, if you choose a different direction for IP, you get a different sign from mine. If you have the same direction of IP as mine, you get the same answer as mine. Let's say over here I have a negative answer, right? So that means by if you choose your direction of current for IQ to be to the left, then you get a positive answer. If you choose your direction of IQ to the right, then you get a negative answer. But I think both should be accepted because they don't assume the direction for you. You are the one assuming the direction. So they should accept both positive sign and negative sign as well. Okay, done with question C. Now let's move on to question 4. Okay, well, I guess it's quite difficult to do a 2 hours paper. It's quite difficult to talk for 2 hours straight. Let's continue. Okay, a circular coil of 100 turns with a plane area of 8 times 10 to the power negative 3 meters square is placed in the magnetic field of 0.2 Tesla. Okay, circular coil, 100 turns, plane area 8.00 times 10 to the power negative 3 meters square, magnetic field 0.2 Tesla. Calculate the magnetic flux linkage, okay, very clear the question, through the coil when the plane of the coil, okay, the plane of coil makes an angle of 0.8, make an angle of 30 degrees to the magnetic field. Okay, angle of 30 degrees to the magnetic field. That means by, if this is my coil, okay, looking at it from this angle, if this is my coil, this coil has 100 turns and it has an area of 8.0 times 10 to the power negative 3 meters square, and the magnetic field is 0.2 Tesla, but it makes an angle of 30 degrees to the plane. So means by the magnetic field might be like this, and the angle between the plane and the magnetic field is 30 degrees. This magnetic field, the angle with the plane, this is the plane, it's 30 degrees. Okay, now they ask for the magnetic flux linkage. Well, magnetic flux linkage, you should refer to the equation. Okay, we are in chapter 5 right now. So magnetic flux linkage will be big phi is equal to n small phi is BA cos theta. Okay, so let's do it. Question 1, big phi is equal to n small phi, where small phi is equals to BA cos theta. Okay, so it's relatively straightforward. Number of turns is 100. Tesla, how many Tesla? 0.2. Area is 8.0 times 10 to the power negative 3. But here's what many students got it wrong. Okay, this theta here is the angle between B and A. But you have to be very careful. Area vector here, the direction is perpendicular to the plane of the area. Okay, that means by right, for this situation here, the plane, the area vector will be pointing this direction. This is the direction of A. Okay, because your plane is like this, and I said here it has to be perpendicular. So the direction will be pointing out from the plane or into the plane. But usually we choose the one that follows similarly the direction of magnetic field. So in this case, we point outwards. Okay, so when we say angle between B and A, that means by we are interested with this angle. This is theta. But we know that this is 30 degrees, right? And we know that this is perpendicular. This is perpendicular, and you know 30 degrees. So technically, you know that what happens over here should be theta is 90 degrees minus 30 degrees to get 60 degrees. Okay, so to calculate it, this will be 100 times 0.2 times 0.0 times 10 to the power negative 3 times cos 60 degrees. Then you get 0.08. That's your magnetic flux linkage. Unit is in Weber. Okay, next, the coil is rotated about an axis of rotation perpendicular to the uniform magnetic field. at a constant speed of 10 revolution per second. Okay. Interesting. Okay, the axis of rotation is perpendicular to the uniform magnetic field. So perpendicular means by, okay, there's many ways to be perpendicular, but in this case I think because the syllabus is not that complicated, what they say regarding your axis rotation is your axis of rotation, it's here. Okay, that means by your plane will rotate like this. Okay, we don't want to complicate matters. There are other ways to be perpendicular, but I think your syllabus only limits you to this way of rotating only. Okay, so this is the axis of rotation. So you're going to, if this is your coil, where can I get a coil? Okay, if this is your coil, right, then your axis of rotation is something like this. This is your axis of rotation, and rotate like this. Then your magnetic field is like this. Okay, and rotate like this. Okay, don't want to complicate matters. There are other ways of putting axis of rotation, but I don't think that's what they're asking for. Okay, so in this case, they ask for the maximum, value of EMF induced. Okay, this is a rotating coil situation. Okay, I won't go through the details too much, but if you are in a rotating coil situation, this would be the equation to use. But because they are asking for maximum, right, you know that when it's maximum, sine omega t will be equals to 1. Okay, sine omega t will be equals to 1 for maximum situation, so we can change it to NAB omega. Okay, the equation is NAB omega sine omega t. But when, what am I doing? When epsilon is equals to epsilon max, you can make a statement saying that sine omega t will be equals to 1. Therefore, omega max is equals to NAB omega. N is again 100, area is again 8.0 times 10 to the power negative 3. Magnetic field is 0.2 Tesla. The problem is omega. We know that omega here, they say is 10 rev per second. Okay, but we know that in our calculation omega has to be in radian per second. So let's change it. 10 rev per 1 second. You want to eliminate the revolution, you want to change it to become radian. So you know that 1 revolution is equivalent to 2 pi radian. So that makes it to become 2 pi multiplied by 10. Then you can remove the revolution. Your left is radian per second. So here you can substitute 2 pi multiplied by 10 revolution. Okay, so if you do everything here, okay, you get your answer to be equals to 10.05. Okay, EMF volt. Okay, so that's how you obtain the maximum value of EMF induced. Okay, let's continue. B. X and Y are two adjacent coaxial coils. There are two coils. Most likely it's mutual inductance question because there's two coils involved, but let's continue first. The number of turns of coil X and Y are 100 and 1000 and 5000 respectively. Okay, so let's probably sketch out the situation. You have one coil, coil X. They didn't specify the coil is let's don't complicate the situation. Think simply. Okay, let's look at it from front view. Front view have one coil. This is coil X. Okay, coil X, the number of turns is 1000. Okay, then also at the same time, coaxially there's another coil. They share the same axis. So it's coil Y, and Y will be equals, and Y is equals to 5000. Okay, each turn of coil X produce a flux of 8.5 times 10 to the power negative 5 Weber. So this is specific for coil X. Okay, so flux each turn, so it's without linkage. This is 8.5 times 10 to the power of negative 5 Weber. Okay, how much current is flowing through it? 3 ampere. Okay, this is all for coil X. Okay, each turn of coil X produces a flux of blah blah blah. So this flux is produced by coil X because there's current flowing in coil X. There's current flowing here. That's why there's magnetic field produced by the current. And the magnetic field also passes through the same coil, coil X. That's why there's magnetic flux over here. Now they ask you to find a self-inductance, but for which coil they didn't specify. Well, it has to be for coil X because there's no current flowing for coil Y, so it has to be for coil X. Okay, so what's the strategy that I use for this kind of question involving self and mutual, right? Okay, self and mutual is over here. Equation from here to here are for self. Equation over here is for mutual. What I do is I split into two parts. Okay, this is used when you have situation where you have changing current. If your current is changing, then yes, you can use this one. But if your current is not changing, then you have to stick to 49 to 51. Not changing. Okay, constant current. Okay, so this is a equation which is general, used for any kind of coil or solenoid. You can use this equation, but these two are specific equation. Okay, only specific for coil or solenoid. Okay, for this situation, because the current, if you look at the question, the current is not changing, so we will not be using this equation. We'll be following either 49 to 51. Okay, but I believe you don't have all this information, right? So most probably it's 49. Okay, let's look at it again. Self-inductance, again, they give you the flux, they give you the current, but they don't give you all the area, everything, right? So you have to stick to the general equation, and the general equation will be Lx, in this case, will be Nx phi x divided by Ix. Everything has to be on the same coil because you're calculating self-inductance. So Nx is 1000, phi x is 8.5 times 10 to the power of negative 5. Ix over here is 3. Okay, so let's put it in. Zero 0.0283. Okay, unit for inductance will be Henry. Okay, next, energy stored. Energy stored is U is equals to half Li squared. You can refer to the formula sheet for it. Okay, you get your L from previous question. Put it in. The current is 3 ampere. Then you get 0.1275 joule. Okay, very straightforward question, but I think it's a bit trying to mislead you because they tell you that there's two coaxial coil, which might lead you to think that it's a mutual inductance question. But even though there's two coils, right, they're only focusing on what happened to one coil, which is coil X. The current is flowing through coil X. It causes a magnetic field produced by coil X, and the magnetic field passes through coil X itself. That's why coil X itself has a magnetic flux. Everything is related to coil X. They are not really interested in coil Y. So that's why coil Y, the value for NY is not really used here. Okay, so that's for this question. Next, we have question 5 over here. A coil have an inductance of 0.14H and resistance of 12 ohm connected. Let me zoom in first, or else you cannot see the question. A coil having an inductance of 0.14 Henry and a resistance of 12 ohm connected across a 110 volt and 25 hertz line. Let's sketch it out. Okay, there's only a coil connected to a power supply. So let's sketch it. There will be a coil. This coil is connected to a power supply, but this is an AC power supply because they give you the frequency. So you have to draw an accumulator instead of a DC power supply. This coil here has both inductance and resistance. So the resistance is 12 ohm, but the inductance L is 0.14 Henry. Okay, now what about the power supply? It's a 110 volt power supply, but because they didn't specify this is peak voltage or RMS voltage, right? Then under the situation where they don't specify, it will be RMS voltage. Why? Because RMS voltage is the one which is more representative of the sinusoidal voltage. Okay, so usually when we don't specify its peak, that means it's RMS. Okay, if we specify its peak, then only it will be peak. Okay, so VRMS is equals to 110 volt and the frequency is 25 hertz. Okay, so this is an RL circuit. Even though there's only one coil, this is an RL circuit. What I usually do is I will sketch the phasor diagram first. So for this situation, because it's RL, if your current is pointing in this direction, what else do you have? You have your V across R, V across the resistance to be pointing in this direction, and you have your V across L to be pointing in this direction. Okay, you can also sketch a reduced version of everything. Reduced version means by you divide everything by I. Okay, so in that case, your phasor diagram is no longer a phasor diagram if after you divide by I, but if the current is pointing here, then you are left with resistance over here, you are left with XL over here. Why do I know? Because V0 R is equals to I0 R, V0 L is equals to I0 XL. So if I divide everything by I0, then divide by I0 means by divide by I0 you get R over here. Divide by I0 you get XL over here. Okay. Continue on some theory. If you combine these two over here, what you get here is called overall voltage. Okay. So V0 is equals to I0 Z. Okay, so from here you know that if you combine the inductive reactance and the resistance together, the combined value over here is called impedance. Okay, then the angle over here is usually called phi, the phase angle. Okay, that's the idea. Usually I sketch the diagram, I sketch a phasor diagram before I start to do the question. So let's look at the question. First, they ask for the current in the coil. You have V, you want I, so most probably you have to use VRMS is equals to IRMS, but this will be multiplying it by Z. Okay, you have to know that VRMS, this equation here is for the overall circuit. Okay, but if it's VRMS R, it will be equals to IRMS R. This will be for the resistor. If it's VRMS L, it will be equals to IRMS XL, which is for the for the inductor. VRMS C is equals to IRMS XC. This will be for the capacitor. Okay, so for this situation, we are going to use the first equation over here. So VRMS is equals to IRMS Z. So you have to find Z. Z is equals to R square plus XL minus XC. I'm not referring to the equation because I'm a bit in the rush actually. So you have XC here will definitely equals 0 because there's no capacitance. So you need to find XL only. So XL is equals to 2 pi F multiplied by the inductance. 2 pi frequency is 25, inductance is 0.14. This allows you to find the inductive reactance. Oops. 2 pi times 25 times 0.14, that's 7 pi. Okay, unit for inductive reactance is ohm. Okay, so once you have this, you can substitute inside here to get your impedance. R is 12 ohm, XL is 7 pi minus 0 square. Okay, so this will allow you to get your impedance to be 25.05 ohm. Then now you have your VRMS, which is 110, IRMS, you have your Z, which is 25.05. So from here you are able to get your RMS current to be equals to 4.39 ampere. Okay, whether they're asking for current or RMS current or peak current, well, they didn't specify. For a situation where they don't really specify, then this should be RMS current. Okay, so that's question A. Next, question B, the phase angle. Phase angle is this angle over here. You can see that it can be found using various ways. You have your impedance, you have your XL, you have your R. You have all three values here. So technically trigonometry allows you to use many different methods to find it. Okay, let's use tangent. If you use tangent, then this will be the opposite side, this will be the adjacent side. So tangent phi allows you to know that it's opposite divided by adjacent. Opposite here it's XL, adjacent here it's R. Okay, opposite is not Z, opposite is XL. You can bring the XL arrow to this side to form a right angle triangle, right? For this right angle triangle, the opposite side is XL. Okay, so now it's just substitution. Phi is equals to inverse tangent. XL is 7 pi. Resistance is 12. So from here, oops, you get 61.4 degree. Okay, so that's your phase angle. Phase angle, positive, negative, for me is important. If it's positive, means by the overall voltage is leading the current. If it's negative, then the current is the one leading. Okay, so for me, the negative sign or positive sign is important, so I do modulus it. But certain lecturers prefer to modulus it because they just need the value of the angle without the sign. Okay, but for me, I usually keep the sign. Okay, so XL here, it's positive because it's pointing upwards. If it's XC, it's negative, then you have to put negative XC. Okay. Oops, I'm really in a rush right now. Next, question C is power factor. Power factor is just cos phi. You have your phi already, so put in cos 61.4. So cos answer is equals to 0.479. Without unit, no unit for power factor. Last question, power loss. Power loss is usually happen because there's resistance inside, so you can calculate it using VRMS, IRMS. Okay, VRMS, IRMS. Okay, VRMS is 110. Oh, there's a cos phi, of course. Cos phi, don't forget the cos phi. Okay, VRMS, RMS, cos phi. So 110 multiplied by IRMS 4.39 multiplied by cos phi. Phi just now is 61.4. So 110 multiplied by 0, right? So you get 2311. Okay, so that's your average power, also known as the power loss in the coil, because power loss through the resistive component. This cos phi here allow you to focus on the resistive component. Okay, because as you can see here, resistive cos, you only focus on the resistive component. Okay, so that's it. That's question 5. We move on to question 6 after break.